Okay, so thanks all for coming. So on Thursday, there is, of course, midterm 2 coming up. Very exciting and hopefully fun. The midterm is now written. I'm pretty confident given the time we're now allowing for it and the time we're giving for you guys to upload it and so on, hopefully people should feel under a lot less time pressure, a lot more time to really think about the problems and play around them, figure them out and so on. So that's good. I will have a extra office hours that will be tomorrow, so Wednesday at 4 p.m. Just because my usual office hours will be Thursday, which is of course when the midterm's happening. Otherwise, yeah, any questions, let me know. But I think you guys should know the drill from midterm 1. You have all day Thursday to take the exam whenever you want to, 2.5 hours maximum to submit on Gradescope. Okay, so last time we covered a lot of content, a lot of fairly technical content on quantum Shannon theory. And in particular, we talked about how if you have a large number of copies, a large number of quantum states drawn from some ensemble with density matrix rho, then the sort of rate at which they can be compressed, the number of qubits needed per state that you have is in that limit S of rho, the von Neumann entropy of the density matrix. And we also talked about the classical capacity of a quantum channel N, and what you would like that to be, the sort of nice answer everyone hoped it was there would be what's called the Halevo information of the channel, chi of N, which is the max over sort of quantum classical states. I called this X in the lecture. Rho X tensor XX. X is the classical label of which state you prepare. Rho X is a density matrix. You need a PX here of the mutual information between B and X for the state. We'll call this whole thing rho AX for the state N acting on rho AX. Okay, so that almost fell off the side. But yeah, it's the amount of correlation you can create between an input to a classical choice of input to the channel and the output to the channel. Unfortunately, this isn't quite true. And instead, the answer is that it's the limit as n goes to infinity of 1 over n times this Halevo information for n copies of the channel. Okay. So it doesn't have a sort of simple practical form you can find out, unlike the version for a classical channel. Okay, but we're going to leave quantum Shannon theory there. Hopefully, some of you may get interested enough to learn the more general theory, quantum capacities of quantum channels, and so on. But for today, we're going to talk about something a bit simpler, hopefully, which is sort of continuous time evolution of open systems, and systems that are interacting with some environment. Okay. So for closed systems, if I have some isolated quantum mechanical system, then as we all know, time evolution is described by unitary matrices. Okay. In particular, if you go to sort of the continuous time version where you just want to evolve from time t to time t plus epsilon, we get a sort of differential equation for the state, pure state ket psi. And that differential equation is, of course, just the Schrodinger equation. The I d by dt of psi is some Hermitian operator H acting on psi. Okay. And in turn, if instead we actually have a density matrix to start off with, then there's also a differential equation for rho, which is basically the same. I d by dt of rho is actually the commutator of H in rho. Okay, just plug in rho equals psi psi, or sum over I pi psi I psi, and you know, apply the Schrodinger equation to each of the psi's, the ket psi's and the bra psi's, and you'll get that formula. Okay. So what about open systems? Well, we know if we start with some open system in some density matrix and it interacts with some environment that it's uncorrelated, then the sort of total evolution from the initial state to the final state is described by a quantum channel. Okay. That's the sort of replacement for a unitary matrix when the evolution is open, and so it's interacting with some environment. So the natural thing to ask is there then some differential equation for rho that describes how to evolve rho from rho at time t to rho at time t plus epsilon, right? So, you know, be in general, sort of d rho by dt is going to be sort of some function over rho. And the answer is that in general, this is not actually possible. In fact, it's never possible to, it's never true exactly. Reason for this is the following. So let's say we have some system as, okay, we're going to have our system be 1 qubit. It's going to start in the state psi, and our environment is going to be 1 qubit, and it's going to start in the state 0. Okay, and we're going to have the unitary, sort of the two together are going to be a closed system. Just the system on its own is going to be open because it's interacting with the environment qubit. And there's going to be some unitary describing time evolution by time t. And that unitary is just going to be a swap gate. Okay, so for time evolving forward by time, this fixed time t is just going to act as a swap. Okay, so let's evolve the state forward by time t. No matter what psi is, the state is then going to be A in the 0 state, psi for the environment. Okay, and in particular, that means rho A at time t is just going to be 0, 0. Independent of our starting rho, which was like psi psi. But now we're going to evolve it forward for another time t, and it's going to do another swap. We're going to end up back with psi of A 0e. So rho A time 2t is going to be psi psi again. So what happened is that rho A at time 2t depends on the initial state, rho A at time 0, even though rho A at time t didn't depend on that at all. Okay. the map from rho A, so the map from rho A0 to rho AT, or from rho A0 to rho A2T is described by a quantum channel, but the map from rho A at time t to rho A time 2t is not described by a quantum channel. In fact, it's not a, in this case, it's not even well defined at all. Right, because we have the same state at time t going to different states as time 2t. In general, there will be a well-defined map. But it won't be a quantum channel. So rho AT rho AT plus epsilon is almost always, the exceptions like the one above, but it's not a quantum channel. And the reason it's not is that information is flowing back from the environment into the system. Okay, so in a quantum channel, we assume that the initial state of the environment is fixed, so it has no information. So information can only leave the system, it can't come into the system. But when you have time evolution for an extended period of time, then information always escapes, and then that information is sitting there in that environment, and then it can end up coming back in. Okay. Okay, so having said that there's no way in general to describe the evolution from rho AT to rho AT plus epsilon by a quantum channel, I'm now going to spend the rest of this lecture doing exactly that. Okay, and the reason I can sort of get away with doing exactly that is that if the environment is big enough, sort of a big enough, complicated enough system, then information in the environment is very quickly forgotten. Okay, and what I mean by forgotten is sort of distributed among a huge number of degrees of freedom in some complicated way. Such that it's never going to get back into the system. Okay, so this happens in a time that I'm going to call delta t forget. So what this means is so long as we sort of coarse grain the state, we only care about the state, we're looking at timescales delta t that are sort of much larger than this time for the environment to forget anything that falls into it, then we can basically think of each step of evolution rho, the step evolution from rho of t to rho t plus delta t as an independent quantum channel, right? Where the information that escapes. So in the first time delta t, we just have some quantum channel and subscript delta t that describes that evolution. But then all that very, very quickly, the information that escaped out in that time delta t gets forgotten by the environment. It gets completely lost into, escapes as photons radiating off to infinity. It disappears into complicated correlations of some like material or something. It gets dispersed, dissipated, and the next step of evolution can be thought of as just an independent channel. So we can think of it as as we get like a clean copy. It's maybe a good way to say it. Clean copy of the environment. Every sort of delta t forget, right? We just get replaced with a new environment that has no memory of the information that fell into the old environment. Switching in like different environments for it to interact with. Okay. So this is just an approximation, but it can be very good in certain circumstances. So we're just going to go with it, and we're going to see the evolution that it describes. Okay. So we're going to look at we then need to look at timescales that are themselves much longer than the delta t over where this approximation is valid. So if we look at times t themselves much bigger than this delta t, where each step we have an independent channel, then evolution of rho is approximately described by a differential equation. Okay, so our aim for the next while is going to be to understand what that differential equation is, just using our knowledge that our assumption that each little step of the evolution is described by some quantum channel. Okay, any questions about that?
Can I ask a quick question about something you said before?
Yep.
So you're saying that you almost always have a well-defined map on the density matrices for rho of t to rho of t plus epsilon, but it might not be a quantum channel.
Yep.
Presumably, if it's a well-defined map, then it's trace preserving and linear. So is the completely positive
it's the completely yeah exactly
a good way of seeing why that has to be violated in this?
Think of so imagine rather than involving for looking at rho a at like exactly t, right? We looked at like rho a at like t plus epsilon, right? Then the reduced density matrix of A will depend very slightly on the initial state, right? And in fact, the map from the initial state to the density matrix at time A is like an invertible map, just generically maps to invertible, right? And that means that if we have an invertible map, then we can just map back from rho at time t plus epsilon to rho at time 0, and then map from rho at time 0, there's a quantum channel to rho at t plus 2 epsilon, right? The problem, of course, is that invertible map is, the reduced density matrix at time t plus epsilon is like almost 0, 0, right? It's tiny differences depending on what the initial state was. And so that map of reversing time is like blowing up the differences between the states. That means it can't be positive, right? Just because, if I have something that like makes the differences between states bigger, then if I have the identity plus a little bit and the identity sorry, if I have a map that makes differences between states bigger, it can't map all positive states to positive states. That's a general fact. Does that answer your question?
Yeah, I have to think about it a little bit, but
yeah. There's a whole literature on non-Markovian master equations that basically mean doing exactly that, but they're a bit dodgy because they're just like using the fact that at any time t, the state generally, in principle, there's an invertible map from the initial state to the state at any time t, and then you just invert that and then, roll it forwards to get the new thing. So they're very dodgy. Like that comment was really made just for accuracy rather than because it's an important point.
I see. Interesting. Thank you.
Okay. The important point is that information is flowing back in general, and so it's not just a quantum channel. Okay. So we're going to assume that this differential equation is true. So we're always going to have that rho t plus delta t is going to equal some n delta t acting on rho of t. Okay, and for the differential equation to be well defined, then this change that happens in t delta in this small time evolution needs to be small. So this needs to be this sort of the original rho of t plus some order delta t correction. Okay. So turn, that means that this channel n of delta t needs to be just the identity channel plus delta t times some superoperator L, which is often called the Lindbladian. Okay, this is just exactly the same way that we went from a unitary U to writing it as the identity plus IH. Okay, so this gives us a differential equation. It's just that delta rho by delta t, I didn't even need to make it partial rho, it only depends on dt, but never mind, is going to be this superoperator L acting on the state rho. Okay, often can assume that L is time independent, just like for the Schrodinger equation. The dynamics are independent of time. Then this density matrix has a solution, just given by the limit n tends to infinity of sort of the identity plus t over n times L all to the power n acting on rho at time naught, which of course we can write using usual notation. It's just e to the Lindbladian times t, all acting on rho naught. Okay, that's just a sort of formal statement. But this differential equation, it's a first order differential equation for the matrix elements of rho. This is something that can easily be solved on a computer or whatever. Indeed, often it will have just an explicit analytic solution. Okay. However, this channel n delta t always has some Krauss representation. And that's going to allow us to be a bit more explicit about this Lindbladian L of t. Okay. So let's consider some particular Krauss representation for n delta t, which we can write. So rho t plus delta t can be sum over I, ki rho, ki dagger, and again, rho t is equal to rho t plus order delta t. Okay, and we're also going to need to use the fact that we require sum over ki dagger, ki to be equal to the identity. Okay. So because we need to get that rho of t sitting there, we need one of these KIs. So yeah, we're just going to match this order by order. Okay, so it's first order, we have zeroth order, then it's just the identity. How do we get the identity? We have K0 equals the identity, Ki equals 0 for I not equal to 0. Okay, but that's not enough because we also need to get the order delta t correction. Okay, so the leading correction here has to be order delta t. What can that come from? Well, there's two things. We can add an order delta t thing to K0, right? So that will then, give an order delta t contribution to rho of t plus delta t from one of these, the K0, K0 having the order delta t thing and K0 dagger having the identity. So this is in general just the identity plus delta t times some operator, but it's going to be convenient to split that operator up into its Hermitian and anti-Hermitian parts. So to write it as minus IH plus K times delta T, where K and H are both Hermitian. Okay, so we just had some generic operator times delta T, but we just split that operator up into its Hermitian part, K, and its anti-Hermitian part, minus IH. Okay, again, just assigning letters to things. What about the KIs for KI not equal to 0? Well, if they're going to give an order delta T contribution, then we actually need the KIs themselves to be order square root delta T, right? Because otherwise, the correction we'll get will be from KI rho T KI dagger, and that will be order delta T squared. So these things need to be order square root delta T, and we're just going to call them square root delta T times Li for some operators Li. Okay. So we're now getting close to just having a general form of what things look like. But we still need to remember that there's a constraint, which is that even including the first order corrections, we need the sum over all i's of Ki dagger Ki to be equal to the identity. Right? Sorry, to equal the identity. So what is this? Well, we have K0 dagger K0. Okay, so that is, well, we have the identity. We have K0 dagger, we have plus IH plus K times the identity, and Ki dagger Ki, we have the identity times minus IH plus K, right? So those are the three terms we get. And we see immediately that the H's are going to cancel out, and it's just going to be the identity plus 2K delta T. Then finally, we're going to get the contributions from I not equal to 0, which is just going to be Li dagger Li times delta T. Okay, you get a square root of delta T from each one. Okay, so subtracting the identity from each side, we get the 0 is equal to 2 K delta T plus sum over I greater than or equal to 0 of Li dagger Li. In other words, we have K minus a half. Sum over the I is greater than or equal to 0, Li dagger Li. Okay, this gives us our general form d rho by dt, the Lemblavian L of rho. So So what are the contributions we have? So it's equal to sum over I, ki rho, ki dagger minus rho. Okay, so the contribution from K0, the identity part cancels out. We get minus IH rho minus a half sum over I greater than or equal to 0, Li dagger, Li rho. So that came from the K0. Also have the contribution from the K0 dagger. So this is going to be plus IH rho, but then again, minus a half Li dagger Li. So minus a half rho Li dagger Li. And finally, we get the contribution from the KIs not equal to 0, which is just going to be sum over I Li rho Li dagger. Okay. This should all have been divided through by delta t. We're working out the derivative. Okay. Let's put this into a neater form. It's minus I times the commutator of h and rho plus sum over I greater than or equal to 0. Then we have three terms that involve that sum. An Li rho Li dagger minus a half Li dagger Li rho, and we have minus a half rho Li dagger Li. Okay, so this whole equation is called the Lindblad master equation. It's a bit of a pretentious name if you ask me, but it is nonetheless an important equation for describing the dynamics of open systems. But I think given that it's only ever an approximation to what's really happening, calling it the master equation is a bit full of themselves, but yeah, I don't know who came up with that, I have to admit. Okay, any questions about how that derivation works? So there's a question in the chat actually about whether L can depend on time. The answer is in general it can, right? Like you could imagine that this is some quantum computer and we're dialing the settings on our quantum computer. We're changing the Hamiltonian that's interacting the system with its environment and so on. And in that case, L will definitely change it with time. But often we deal with a simple situation where the dynamics are time independent, and in that case it won't. Okay, and that's what we need. We need that assumption here to give this simple solution here. But in general, it can depend on time. Any other questions?
I had a very quick question.
Yep.
You had a 1 over delta t in this final expression, or at least in the top line. Did it get absorbed into?
I put that in because I forgot to include it. Let me write it a bit more neatly. That's because all the terms I was writing down here, right, were like the order. They're all the delta t terms, right? So we had a delta t here, right? It was really minus IH delta t and K delta t and so on. And similarly with the LIs, you had a square root of delta t from the Ki and a square root of delta t from the Ki dagger. So that made it all order delta t. Like the change, you know, just the stuff in the square brackets is it's rho t plus delta t minus rho t of t, right? To actually get the derivative d rho by dt, you've got to take that and then divide by delta t and then take the limit of delta t goes to 0.
Okay, perfect, thanks.
Of course, we can't really take the limit of delta t goes to 0 because if we take delta t too small, then our approximation, yeah, I should have set up here actually. The approximation that rho of t plus delta t is just determined by rho of t and not anything at all before is called the assumption of Markovian dynamics. Okay, and this is only valid when you sort of only look at timescales much longer than the forgetting time of the environment. So the term Markovian comes from what I call Markov chains and classical probability. It just means some sequence of like, x of t, x of t plus 1, x of t plus 2, and so on, 3, 4, where for any t, then x of t plus 1 only depends on x of t. It maybe depends stochastically on x of t, but it doesn't depend at all on like x of t minus 1, t minus 2, and so on. Okay, but don't worry about that. It's just a word that describes this approximation.
I have one more question. So suppose we had started off with not such a great choice of Krauss operators, such that we had multiple zeroth order terms, say, like multiple different terms proportional to the identity at zeroth order. Can we always necessarily change Krauss operators so that we have it of this form?
Yep. Yeah. So we could have. We could have, for example, made K0 be half times the identity, and K1 be a half times the identity, and K2 be a half times the identity, and K3 be a half times the identity. Those Krauss operators, so those zero order Krauss operators will be related to the one we used, where it's just K0 is the identity, by just some unitary rotation, right? So you could then find the first order corrections to those Krauss operators, and then do the same unitary rotation of that on them, and you would get something that would necessarily be in this form. But it would be more complicated to find the like most general form of the allowed corrections that give a first order correction to the state. So this is a much simpler set of Krauss operators to think in terms of. Any more questions?
I can ask a question about H and L. So H probably has interpretation on Hamiltonian. Does L has interpretation something similar to Lagrangian?
No, it's the L's are nothing to do with the Lagrangian. The H we're gonna discuss in a minute. Indeed, can be thought of as the Hamiltonian for the system. The L's, it might stand for Lindblad. I don't know. People use L. My guess is it stands for Lindblad. Yeah. Okay. So that nicely brings me into the sort of next thing that I want to talk about, which is really just what all these different terms mean, right? This is a pretty complicated equation. So we have these sort of 4 different terms. These last 2 terms are pretty similar. So maybe 3 different terms that contribute to the evolution of rho. Okay. So the first one is just going to be minus I times the commutator of H and rho. As Zhilang rightly pointed out, right, this is just the d rho by dt equals minus I times the commutator of H and rho. That's the equation I said at the very beginning for just unitary evolution of rho using some Hamiltonian H. Okay, so this just describes the sort of isolated evolution of the system without ignoring any interactions with the environment. Okay, so the second type of term we have is just this sort of Li rho Li dagger terms. Okay, and so Li here is basically arbitrary. We really didn't have any constraints on Li, right? The Ki's had to add up to the identity, but that just ended up giving us relationship between this thing K and the Li's. So Li's are arbitrary, completely arbitrary operators. And you can, roughly speaking, think of this as describing sort of small possibility of an instantaneous quantum jump happening. So if you think of rho as describing an ensemble of possible states, then there's some chance that in between time t and time t plus delta t, then just some instantaneous operator Li gets applied that just completely changes the state rho to the new state Li rho Li dagger. Okay, so yeah, if rho is an ensemble, then there's some probability that just psi just instantaneously gets mapped to Li psi. And that jump is caused due to interactions with the environment. In fact, if you assume that rather than just like the environment is left to just sort of evolve on its own, then you assume that sort of the environment is being constantly measured. This sort of heuristic interpretation that there's some small probability of just a sudden change in the state from rho to Li rho to Li dagger is sort of literally true. So what happens, there's some small probability that you measure some sort of different state for the environment from the original state. So the environment started in the state ket 0. There's, if you have a little bit of time evolution, there's only a small probability that it isn't in state 0 at the end of it. But if that happens, if you get that measurement outcome, then that will instantly update the state from rho to something totally different, which in this case will be like Li rho, Li dagger. I
have a quick question.
Yep.
I just thought intuitively that if you did constant measurements, you were guaranteed to never have any change in your state.
Yeah, that's yeah. So that's why this sort of Markovian dynamics is only ever an approximation. So like for the Markovian dynamics to be true, we need to be like switching out a new environment every time. Okay. And if you really take the limit where you're just like constantly switching in a new environment, and you never have any the time is order like really tiny, and you have the same Hamiltonian each time, then there's never actually any interaction with the environment. And the same thing is true as if you're measuring, because you're measuring so fast that there's no time for a change to happen. So that's why we need to have our delta t's be long enough that there's some time for it to like actually interact with the same environment, which is not going to be Markovian, and there's some probability of information flowing back into the state. But then there's some time scale where the environment forgets everything, and we can think of it as being a new environment. So the measurements need to happen not too fast. The measurements need to happen on order like delta t time scales, which has to be much bigger.
We consider like continuous time on just to be time scales longer than this forgetting time.
Yeah. You should think of this the Lemblanc master equation as like describing a Brownian motion or something like that, right? The fact that you have these square root delta t showing up these things, right? That's a classic signal of something like a Brownian motion, where what's happening is you're having a lot of very fast, like bouncing back and forth, and that's causing a gradual drift, right? But it in this approximation where the distance it travels, the probability of these KIs are getting rated by square root delta t. You can't really take the limit as delta t goes to 0 and have that make sense. So instead, there has to be some fundamental timescale. Brownian motion, it would be the time between like the little dust particle or whatever hitting an atom and like bouncing off it, and the timescale between the bounces. But you just assume that timescale is really, really, really small, and you look at timescales much longer than that. And on timescales much longer than that, it looks like this, like not smooth differential thing, but like stochastic differentiable thing. That's a lot of fancy words, but yeah, the point is that there's always this is only ever like approximate coarse grain description of what is happening, and you need some like fundamental minimum timescale to have it really make sense. Okay.
Isn't information leaking into the environment also like the system interacting with the environment?
Yes. But if the system is interacting with the environment for sort of an extended period of time, then information can leak back and then flow back in, right? And so that's very problematic, because that means that your evolution between the intermediate time where it had flown out and the later time where it had flown back in, come back in, is not described by a quantum channel, okay? Because there's new information coming into the system. So that means you can't describe it in this nice simple way of like evolving for infinitesimal time step by infinitesimal time step. So what you need to assume is that the environment really, really quickly forgets the information that's escaped into it, and so when you look at the interaction with the environment over longer timescales, then information only flows out and doesn't flow back in. But this is only ever an approximation. It's only ever valid on longer timescales. If you try to take it literally, you just have any, you just take the limit as delta t environment forgetfulness goes to 0. Then you end up concluding that no interaction ever happens, for the same reason that in the quantum Zeno effect, you can never have the state change if you're constantly measuring it. I'll answer your question.
So, like, sorry.
I think I have one question.
Yep.
In this approximation, Li are arbitrary. So it means that, for example, that I can construct Li such that it changes when I change the Hamiltonian of the subsystem.
Li's that. So I mean you could imagine changing H without changing the Li's, right? Like these are independent degrees of freedom in the sort of the Lindblad-Master equation. But in general, if you change the Hamiltonian, and certainly of the system, and particularly if you change the way it's interacting with the environment, then the Li's will change. That's certainly true. Does that answer your question?
Yes, thank you.
Yeah. Okay.
Sorry, I just wanted to follow up on my previous one. So if you go back to your example with the two swap operations, if like the environment were to forget, and if it was to forget like the state psi.
Yeah, exactly. So
quantum channel.
Yeah. So what you imagine is that after this first U of t happens, but before the second U of t happens, then very quickly, this environment qubit E interacts with some other environment qubit E2, and they get they have a swap that interacts them, and so then the environment is in the 0 state again, and then when we do the second evolution by U of t, then the system just ends up in the 0 state, something like that. right? And then the second step is still a quantum channel because this information has truly been lost and it doesn't then come back in and get back into the system.
So are you saying like the zero state's like
the zero state is just mathematical convenience. It can be any state. But the what you want is just like you want the environment to be big enough and interacting fast enough that anything that sort of leaks out into it, there's like thousands and thousands and thousands and millions of degrees of freedom, and it just moves off into random ones of them. And like the stuff that the system actually ends up interacting with later is just new degrees of freedom that's never interacted with the system before.
Okay.
Does that make sense?
Yeah.
You can sort of derive this Markovian approximation, but it's like a messy derivation. It requires certain assumptions about how things work. So it's a lot simpler to just say we're going to put that in as an assumption and then work out what it tells us about the evolution. Okay, so then we have one last term here, which is this thing minus a half Li dagger Li rho minus a half rho Li dagger Li. Anyone know what this part is? So this is the quantum jump. What's this thing doing? The answer is basically it's sort of subtracting off the part of rho that did the quantum jump, right? There's some probability that the quantum jump happened, and once the quantum jump has happened, then we need to preserve the normalization of the state rho. We need to preserve its trace. So if we're adding in this probability of the state rho having jumped to Li rho Li dagger, we need to subtract off some probability of it just having remained as rho, right? But of course, the probability that it jumped to Li rho Li dagger depends on what rho was. So it's not as simple as just subtracting off a bit of rho. It needs to be like weighted by the probability of that particular part of rho, that particular state in the ensemble did a quantum jump. Okay. But basically, it's just an extra term that's there so that the trace of rho doesn't get bigger over time. Okay. Not super exciting. Okay, so we got about 25 minutes left. What I want to do is just work very explicitly through some examples of like real life Markovian master equations, Lindblad master equations. And our first one is going to be photon emission. Okay. So what we're going to do is we're going to imagine a two-state system where we're going to have state 0. It's going to be sort of the ground state of an electron. Okay. And there's also going to be a state which we're going to call 1, which is going to be an excited state of the electron. Okay, so we have that the Hamiltonian H is just going to be we're going to make the energy of the ground state be 0, the energy of the state 1 be E. So the Hamiltonian is just going to be E, the extra energy from being excited, times projector onto 1, right? But then we're going to have another physics that can happen, which is going to allow the electron in its excited state to emit a photon of energy E and thereby drop down to the ground state. Okay, so this is going to be a quantum jumper operator, L1. It's going to be our only quantum jumper operator. And it's going to involve the state starting in the excited state, state 1, and then dropping down to the state 0. Okay, so this describes the emission of a photon to drop from the excited state to ground state. And this gamma inside the square root is just going to be the rate at which photons are emitted. Okay, which in general, yeah, it's a function of the electron charge and stuff like that. Other stuff I won't get into. Okay.
Quick question: Is the E and the H, that's just the probability of remaining in the excited state?
No, it's not the probability of the remaining. This is just the Hamiltonian of the system, right? So the E is just the energy of the excited state.
Oh, I see. Oh, okay.
The probability of the drop happening is entirely controlled by this L1. Okay.
Thanks.
Okay. So let's work out what rho dot is. The derivative of rho with respect to time. Okay, so we have these three terms here. First is the commutator of H with rho. Okay, so if H is just 1, 1, E times 1, 1, then what does that give you? Well, if rho is initially the state 1, 1, then that commutes with H. Same if it's 0 and 0. So those don't do anything. If it's 1, 0, then we get minus I H rho, so minus IE times let's assume rho is equal to rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1. Okay, and similarly, this off-diagonal term in the bottom corner, we get an IE times rho 1, 0. Okay, rho 1, 0 is actually rho 0, 1 star, but never mind. Okay, so then we have second term, which is just the L1 rho L1 dagger. Okay, so L1 takes the 1 state to the 0 state. Okay, so if we started off in 0, 0, that just gives 0. If we started off in 0, 1, it also gives 0. If we started off in 1, 0, L1 acting on it is fine, but L1 dagger acting on the 0 side, that disappears. Okay, so the only thing we have is that L1, 1, 1, L1 dagger is equal to 0, 0. Okay, it's equal to technically gamma times 0, 0. Okay, so what does that mean? We write that. Actually, we write this whole thing below. So L1, 1, 1, L1 dagger equals gamma 0, 0. Okay, so that means that the change in rho 1, 1 is minus gamma times rho 1, 1, and the change in rho 0, 0 is gamma times rho 1, 1. So the probability is, there's some probability of it shifting from the 1, 1 state to the 0, 0 state. And finally, we have to consider these last terms. So half L1 dagger, L1 rho, and half rho L1 dagger, L1. Okay, what is L1 dagger? Dagger L1, it's just equal to gamma times 1, 1. Okay. So what terms do we have here? Sorry. That term doesn't exist yet. I apologize, I was getting ahead of myself. So the row dot, we just have the contribution from 1, 1 going to 0, 0 to just gamma times row 1, 1. Okay, but we now also have this term from the Li dagger, L1 dagger, L1 times row, which is just equal to the 0, 0, minus a half gamma, row 1, 0, minus a half gamma, row 1, 1. And we have minus a half row, L1 dagger, L1. So the same thing, but with a column rather than row. So 0, 0, minus a half gamma, row 0, 1, minus half gamma, row 1, 1. Okay, so the whole thing have a minus a half gamma, row 0, 1, minus a half gamma, row 1, 0, and minus gamma, row 1, 1. Okay, so in particular, the trace of row gets preserved because the decrease in row 1, 1 is the same as the increase in row 0, 0. Okay, so this differential equation can be solved easily enough. You guys can check. It's just a load of exponentials. But it ends up being, so this bottom right coefficient is just row 1, 1 times 0 times e to the minus gamma t. Top right, we have row 0, 1 times 0 times e to the minus iet minus a half gamma t. Bottom right, it's instead plus iet minus a half gamma t, row 1, 0. And finally, in the top left, it's just row 0, 0 plus row 1, 1 times 1 minus e to the minus gamma t. That's a bit cramped, but let me try again. It's the initial row 0, 0 plus row 1, 1 times 1 minus e to the minus gamma t. Okay, so over time, it's all shifting towards the 0, 0 state. Anyone recognize what this channel for evolving for time t looks like? It's in a bit of a different form. It's actually a combination of two steps. It's unitary evolution by u 0, 0 plus e to the minus iet 1, 1. Right, that's just the evolution if we had no probability of emitting a photon, followed by amplitude damping channel. So recall that the amplitude damping channel sort of suppresses the probability of being in state 1. It's generally written sort of k naught is 1 naught naught square root 1 minus gamma. K1 is naught 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 square root gamma. And that gives us the n of row is row naught naught plus gamma, row 1, 1. Row 1, 1 is 1 minus gamma. The initial thing, then we have a square root 1 minus gamma. Okay, so if we plug in that 1 minus gamma equals e to the minus gamma, capital Gamma times t, then that gives us the suppression of having probability of having the 1, 1 state. Okay, so emission of photons gives us amplitude damping. Any questions about that example, by the way? And I'll go into one last example, and then that'll be the end of the lecture.
For the density matrix, I get like what the diagonal terms like physically mean, but what would the off diagonal terms mean?
Yeah, so it just means, say I started in the plus state, right? If I started in the plus state, say plus plus, the density matrix for that is a half times 1, 1, 1, 1. So how they're changing with time, you know, this e to the minus IET is telling you, for example, that the plus state rotates around more towards like the minus state, right? Like the phase of that changes over time. But we also have the e to the minus a half gamma t. That's just telling you that eventually it's just ending up, even if it whatever it starts in, it's all ending up in the 0 state. So it doesn't matter if it starts in plus or minus, because eventually the off diagonal terms get killed, and yeah, you're just left in the 0, 0 state. Is that clear?
Okay, yeah, thank you.
Okay, so the final example we're going to have is we're going to again consider exactly the same system, but we're going to consider it some finite temperature. So there's sort of, you know, photons floating around at some temperature. It's in like a sort of a black box radiating at some temperature. So we have a thermal bath of photons. That the system can absorb, right? So now it's not that it can only emit a photon and then drop down from the ground state to the excited state. It can also absorb a photon and go up from the ground state to the excited state. Okay, so now we have 3 terms. We have H, E times 1, 1 as before. We have sort of L1 is the emitting a photon. And we have L2, which is the probability of absorbing the photon. Okay, and if it absorbs the photon, it goes up from the ground state to the excited state. Okay. These gamma absorb and gamma emit are actually related to one another. So this emit photon. Absorb photon. Turns out the gamma emit equals, let me do it the other way around. Gamma absorb is equal to gamma emit times e to the minus e over t. Okay, where T is the temperature of the thermal bath, and E is obviously the gap between the 2 energy levels of the electron. Okay. So how does this change things? Oh, not very much is the answer. So let's throw this out pretty big. So all that's happened now is that in addition to having sort of a gamma emit of it going from row 1, 1 to 0, 0, there's also the probability that it absorbs. It goes from 0, 0 to 1, 1. Okay, and then you can check that the off diagonals are pretty much the same as before, except now we have a half gamma emit plus gamma absorb. And row 1. E to the IET minus a half emit plus gamma absorb. Sorry, that's this is rho dot, isn't it? Rather than, I apologize. Let me get rid of these off diagonal terms. They shouldn't be exponentials because this is just the derivative. So this should be minus E, i.e. minus a half gamma emit minus a half gamma absorb, all times rho naught 1, and same thing for rho 1 naught. Okay. So now let's look what happened to this thing in the limit where t goes to infinity. Okay. So the first thing you notice is that these off diagonal terms, they still just have an exponential, okay? So the off diagonal terms tend to 0. What about the on diagonal terms? Well, it's no longer just the case that we're going to end up with rho 1, 1 going to 0 and the state's just going to be in 0, 0. Because we also have if it's in that state, there's going to be probability that it absorbs a photon and then goes up into the 1, 1 state, right? So the on diagonal terms are instead going to reach an equilibrium where the derivative is 0. So what is this equilibrium? Well, it's when the derivative of rho naught naught, and hence also rho 1, 1 is equal to 0, which is when gamma emit times rho 1, 1 minus gamma absorb rho naught naught is equal to 0. Okay. This happens when rho 1, 1 is equal to minus E over T times rho naught naught. So the density matrix rho is actually 0, 0 plus e to the minus E over T 1, 1, except it all needs to be normalized. So it has trace 1. So that gives you a divides through by 1 plus e to the minus E over T. Anyone recognize this density matrix? Come on, someone.
It's a thermal density matrix.
Indeed. So this density matrix can just be written as e to the minus h over t, or more often it's actually written as e to the minus beta times h, where beta is just defined to be equal to 1 over t, divided by trace of e to the minus beta h. So this, right, so this it's literally just the exponential of the operator, right? The operator h was just e times 1, 1. E to the minus beta h is just 0, 0 plus e to the minus beta h times 1, 1. So this is called the thermal or Gibbs density matrix. Gibbs state. And it's roughly the quantum analog of the classical canonical ensemble. Okay, so the canonical ensemble is you just have classical states of energy E, and you have the probability of it being in some state E is proportional to e to the minus beta E. This is just the density matrix version of that. Okay, so yeah, system naturally reaches thermal equilibrium. Okay, so that's all I have to talk about today. Thursday is obviously the midterm, so there's no lecture. Best of luck with that. Should be fine. In terms of what I'd recommend to focus on, just try to really get comfortable working with density matrices and stuff. You go over your quantum computing algorithms, things like that. But like the more comfortable you are manipulating density matrices and dealing with density matrices rather than just pure states, the better. Because that's really the big thing that we've sort of added since midterm 1. So there'll be plenty of stuff on there about that. Next Tuesday, we will be starting to talk about quantum error correction. So don't stop showing up just because there'll be no more exams, or at least don't stop watching the YouTube lectures just because there'll be no more exams, because it's really cool and important stuff. And frankly, it's the key to like why this course even exists at all, because if you didn't have quantum error correction, then like quantum computers would just like not be a real thing. Like it wouldn't make sense to dream of having like proper quantum computers. And it's pretty magical that it exists at all, but it does. So yeah, next 3 lectures will be on that. It's really cool. Any questions about the last part of the lecture?
This might be a dumb question.
Yep.
On the rho 1 0 term, if you do E minus gamma, how does that term goes to 0 as time goes infinity?
So the derivative is proportional to itself, right? So the solution is just going to be an exponential. It's just going to be, it's just going to be like, rho 0, 1 at time t will be just rho 0, 1 at time 0 times e to the minus IET minus a half gamma emit plus gamma absorb
so
times
about
t,
1
right?
0
So you have oscillation, but you also just have exponential decay. So it's going to go to 0.
So about the 1 0 term?
1 0 term is exactly the same. Rho 1 0 is just equal to rho 0 1 star. So it has to follow the same evolution, but it does. It's right. It's again just proportional to itself with an exponent, just with it's IE rather than minus IE because it's the complex conjugate. That just follows from rho being Hermitian.
Yeah.
Cool. Any other questions?
Can I ask another question about why is it called Gibbs density matrix when it's actually canonical ensemble? So there's like canonical Gibbs and grand canonical, those sorts of things.
I mean, there's no pressure there, so like it doesn't matter. Like, probably if we were dealing with chemistry, then you'd have to be a bit more precise about like distinction between the two. But in physics, it's often just called Gibbs state. I agree that's slightly sloppy, but like there literally isn't a pressure or a volume showing up here anywhere, right? So doesn't matter which we use.
Yeah, thank you.
Cool. Any more questions? Okay, awesome. Well, best of luck everyone for the midterm on Thursday.